Okay, back to our objectives here. So we have done the first one, the second one, the third one, and now we're going to do something really similar to objective 2. It's not going to be as complicated as objective 3. It's going to be something really similar to objective 2. We're going to relate liters of one gas in a reaction to liters of another gas in a chemical equation. Like we talked about in the lab, Gay-Lussac's law says that you can use liters as stoichiometric coefficients just like you could use moles. And so let's have a look and see how we work those out. And as we have been doing all along, first off, we have to figure out what are they giving us and what is wanted. Where are we starting and where do we want to end up? So what do we say we're given? Well, we're given 2 liters of ammonia. All right, that's on this side. What do we say we want? We want liters of oxygen. That's on this side. And then we just look up the equation here to see what the relationship is between ammonia and hydrogen. Now, according to Gay-Lussac's law, you can use volume in liters or milliliters, doesn't matter what the volume is. You can use volume as a stoichiometric coefficient just like it's moles. And that's because it's just a unique characteristic of gases. Technically just what we would call ideal gases, but we're going to use it this way today. So this 2 is the 2 liters of ammonia that we are given. And what we want to know is how many liters of hydrogen are produced. And so my relationship between ammonia and hydrogen is 2 to 3. So I'm going to say that for every 2 liters of ammonia, there are 3 liters of hydrogen. And that's going to give us our relationship between the 2 there. And then so if I take 2 times 3 divided by 2, I end up with, no big surprise, same thing we came up with before, I end up with 3 as my answer. But here it's going to be 3 liters rather than 3 moles. Okay, so that's just a unique characteristic of gases that you can use volume in as the stoichiometric coefficients. You can't use grams for solids, but you can use liters for gases, not liters for liquids, but just liters for gases. We'll do another one. How many liters of hydrogen are needed to react with 3 liters of nitrogen? Well, what do they give us? Well, they're giving us 3 liters of nitrogen. That's going to go on the left side. What do we want? Liters of hydrogen. That's going to go on the right side. And let's look at what that equation would look like. I imagine by now this is pretty familiar to you, but we'll just say it again. What are they giving us? And what do we want? In other words, where are we starting and where do we want to end up? Well, they give us 3 liters of nitrogen, so I'm going to put that over here. And what do we want? We're going to figure out how many liters of hydrogen that we produce. And the beauty is all we have to do is look at the stoichiometric coefficient ratio between them to answer that question. So my nitrogen, for every 1 nitrogen, I have 3 hydrogens. So I should be able to say that 1 liter of nitrogen, it needs to combine with 3 liters of hydrogen to produce, when I multiply 3 times 3 divide by 1, I come up with 9 liters of hydrogen. Now keep in mind, this is the same exact appearance when we dealt with moles, but 3 liters is not anywhere near the same thing as 3 moles of nitrogen. 1 liter of nitrogen would have about almost 23 a factor. Let's see. 1 liter of nitrogen is 1 mole of nitrogen would be 22.4 liters of nitrogen. So it's going to be 22. Take. All right, take 2 on 3 liters of nitrogen. So by now you're really familiar with what we're being asked for, and what we're given. But go ahead and put it on the paper, write it down. So what are we given? Well, we're given 3 liters of nitrogen. That's what we're given right there. What do we want? Liters of hydrogen. We can determine the number of liters of hydrogen if we have 3 liters of nitrogen simply by the ratio of our coefficients up here. So for every 1 liter of nitrogen, you're going to consume 3 liters of hydrogen. And so in my denominator there, I will have 1 liter of nitrogen, 3 liters of hydrogen, and now I can solve for liters of hydrogen. 3 times 3, 9, divided by 1 is 9, so I have liters of hydrogen. So I just want to point out that 1 liter of nitrogen would not be the same thing as 1 mole of nitrogen. 1 mole of nitrogen actually has a volume of about 22.4 liters. So 1 mole of nitrogen has a much larger volume than 1 liter. So I'm not trying to say that liters and moles are in any way the same thing. I'm just saying that you can use volume as a stoichiometric coefficient, just like you can moles. All right. Let's do another couple that ought to look pretty familiar. All we're really doing is substituting liters in the equation for moles, but we might as well go ahead and follow through with it. How many liters of hydrogen are needed in order to produce 4.2 liters of ammonia? What are they given? Right there. Start with what we're given. What do we want? Right there. That's what we want. And then what's my ratio in between ammonia and hydrogen? Well, I have 2 ammonias for 3 hydrogens, so if I take 4.2 times 3 divided by 2, that will give me my liters there. Let's look at the next one. How many liters of ammonia are produced if 0.025 liters of hydrogen are consumed? What are they giving us? 0.025 liters of hydrogen. Put that right there. What do we want? We want liters of ammonia. Well, what's my relationship, molar relationship between hydrogen and ammonia? Well, 3 hydrogens for every 2 liters of ammonia. And if I take 0.025 times 2 divided by 3, that will give me my liters of ammonia. All right, so our 6th objective here in Module 6 is to be able to look at a reaction. Like here, we have our formation of ammonia again, and to identify the limiting reagent. Now, we did a lab where we combined vinegar and baking soda in various quantities, and on the front end, baking soda was our limiting reagent, and then the last time we did it, vinegar was our limiting reagent. So you have some experience with that in practice. Now we need to be able to calculate it and determine it mathematically. So there's a couple of ways to solve this, and let me show you how you could go about doing that. So one is look for the smaller amount method, the mole-to-mole way, okay? Here's our question. How many moles of ammonia would be produced if 5.4 moles of nitrogen react with 11.3 moles of hydrogen? Now, always before, we've given you like an amount of nitrogen, but not a differing amount of hydrogen. Sometimes we give you moles of hydrogen and we ask how many moles of hydrogen would be required to produce the ammonia. But now what we're doing is we're giving you either excess nitrogen or excess hydrogen in the equation, and you've got to figure out which. And this is how you can go about figuring out which one is in excess. You can simply solve for the moles of ammonia if you had 5.4 moles of ammonia, of nitrogen, and then solve a different equation for the moles of ammonia if you had 11.3 moles of hydrogen, and whichever of those two is smaller, then you've identified the limiting reagent. So let me put this into practice. So let's say that we have 5.4 moles of nitrogen. We're going to ignore the amount of hydrogen. We're going to say we have all the hydrogen we need there. How much ammonia would be produced? Well, start with what they're given, moles of nitrogen, and now we are coming up with our own question about what we want. That's our wanted. So if I had 5.4 moles of nitrogen, I know that for every 1 mole of nitrogen, 2 moles of ammonia are produced, and I get that from here to here. So that would end up making 10.8 moles of ammonia if I had 5.4. Now let's ignore that entirely. And let's look at this one. Let's say instead that we started with 11.3 moles of hydrogen. Here we have 11.3 moles, and I want to know how many moles of ammonia would be produced if we had that much. And to do that, I know that for every 3 moles of hydrogen, and we get that from here, I produce 2 moles of ammonia. I get that from there. So if I take 11.3 times 2 divided by 3, I get 7.53 moles. So my question is, though, let's say that you start off with 11.3 and 5.4. One of those is going to get used up before the other. And you can tell here, whichever one is the smaller amount, that's going to actually be used up. So I can only produce 7.53 moles of ammonia with 11.3 moles of hydrogen. So that means that my hydrogen is my limiting reagent because it produces less ammonia than my nitrogen. That's one of the ways to answer the question. Let me show you a different way as well. Solving the same exact problem, a little different way, we would do it this way. We're going to look at the formula, and we're going to say that for every 1 mole of nitrogen, I need 3 moles of hydrogen. Okay, so I'm going to start off with 5.4 moles of nitrogen. I'm just going to put 5.4 right there. How many moles of hydrogen would I need for that? Well, I would need 3 times 5.4. Well, I'm going to take that 3 times 5.4, and I come up with 16.2 moles of hydrogen. So what that tells me is that I would need 16.2 moles of hydrogen, but I only have 11.3 moles of hydrogen in order to carry this reaction forward. So I have demonstrated that hydrogen is my limiting reagent because I do not have enough hydrogen to consume all of that nitrogen. And once again, I'll just tell you how I did that. So I assumed that I had 5.4 moles of nitrogen. That's what they gave me right there. So I just put that right up there. But if I have 5.4 moles of that, because the relationship between nitrogen and hydrogen is 1 to 3, I would need 3 times that 5.4 in order to have enough hydrogen. And I don't have that much hydrogen. I only have 11.3. So that's a second way to answer this same exact question. So I'll just summarize this. We haven't done any balancing equations. Just for the simplicity of introducing the material, I've always given you balanced equations. But I can promise you from here on out, you're going to see equations that aren't balanced, so you got to balance them before you ever get started. And then what you're going to want to do is figure out what you're given and what you want, and calculate the amount of product using the given amounts of each reaction or each reactant, and then whichever yields a smaller amount of those two reactants, that will be your limiting reactant in the equation. So that's how you solve the limiting reagent stoichiometric problems. All right, if you hung in here to the end, you're doing well. The very last objective in this module that we want to look at is how to determine the empirical formula of a molecule from its percent composition. And then we can also relate that to its molecular formula. So we did several of these on the quiz that you took, and you guys were able to work your way through them, but let's go ahead and work through some more just to get some practice. All right, here's a question. What's the empirical formula of a molecule containing 65.5% carbon, 5.5% hydrogen, 29.0% oxygen? The way you solve a problem like this is you make an assumption on the front end that the total mass of the compound is going to be 100 grams. You could pick it at anything, but 100 grams just is the best thing to pick because percent means 100. That's what that means. And so if you assume this, you could say this, that molecule contains 65.5 grams of carbon, because we're total 100, and 5.5 grams of hydrogen, and 29.0 grams of oxygen. So if you assume that, now we could say, okay, I know how many grams of carbon, grams of hydrogen, and grams of oxygen are in this compound. Now I could calculate how many moles of carbon, how many moles of hydrogen and how many moles of oxygen are in the compound. And from that, I'll be able to figure out the empirical formula. So here's how we go about setting that up. Carbon has 65.5 grams. Well, how many moles is that? Well, you know how to figure that out. What you are given is 65.5 grams and you want to know moles. And so you will write down 65.5 grams on the left, and then you're going to figure out how many grams there are in 1 mole and calculate the moles. And that's something you've done quite a bit, so I'll just show you what that looks like. So 65.5, there are 12 grams of carbon in 1 mole, so you have 5.46 moles of carbon in that compound. All right, so now we know how many moles of carbon. Let's figure out how many moles of hydrogen. Well, we do the same exact way. You know that you have 5.5 grams of hydrogen, and how many moles of that? You know how to figure that out. You know that there's 1.1 gram of hydrogen for every 1 mole, so you take the 5.5 and you come up with 5.45 moles of hydrogen. And then you also have oxygen as well. So you know that there are 29 grams of oxygen. How many moles of that? You know that there are 16 grams for every single oxygen. This isn't diatomic oxygen here. This is just a compound that has oxygen in it. So I can use 16, not 32. And that gives me a 1.81 moles of carbon. So now I have a complicated, compound with those molar amounts in there. But from that, I can answer my question about my empirical formula. Let me show you how to do that. All right, so we know the elements that make up the compound. He told us carbon, so I'm going to write C there. Hydrogen, I'm going to write hydrogen there. Oxygen, I'm going to write that there. I'm just going to leave it in the same order he gave it to me. And then I'm going to put the moles that I calculated as my little subscripts here. I'm going to say that I have 5.46 moles of carbon. If I get that out there for you. And I'm going to say that I have 5.45 moles of hydrogen. Get that out of there. And I'm going to say that I have 1.81 moles of carbon. Obviously, I'm not going to leave those numbers because I need little simple whole number ratios. I can't leave that. But the way I can figure out a whole number ratio is this. I'm going to figure out which is the smallest of all of those, and that's going to be my 1.81. I'm going to take 1.81 and I'm going to divide every one of these by the smallest, by 1.81. And if I divide 1.81 divided by 1.81, that's going to leave me with 1 oxygen, right? And if I divide 5.45 by 1.81, that's going to leave me with 3. And if I divide 5.46, which is basically the same as this, right? 5.45, 5.46, that's almost the same exact number of moles. By that, I'm going to end up with 3. So this would simplify to C3H3O. That's how you can go from the percent composition to the empirical formula, and that's what that would be, C3H3O. Okay, and one last thing that you can do, you don't know that you can do this yet, but you've got all the information and now answer a really interesting question here. They said that, let's say that the molecular mass of the compound is 110 grams. All right. So earlier we assumed that the mass was 100 grams just because it gave us all of the quantities in percent, but we don't actually know what the mass of the compound is. Here they say, let's assume that let me put it this way, the empirical mass of this compound would have been 100, but what about the molecular mass? Let's answer that. So the way we answer this question is that we go now to the periodic chart and we look up what the molecular mass of that compound would be for 1 mole. So we take 3 carbons, 3 hydrogens, and 1 oxygen and add those up. And if you add C3H3O up, you don't come up with 110 grams, you come up with 55.03 grams. So what that means is that this compound, its empirical formula is C3H3O, but its molecular formula could really be any multiple of that. It could be C6H6O2. It could be C9H9O3. Because its molecular mass is 110, that's exactly twice what the mass would be if it were C3H3O. So you can tell that the molecular formula of this compound is actually going to be C6H6O2. That's how you can go from the molar mass of the compound in that. If the molar mass was 110 grams, you could determine the molecular formula. All right, so we've landed this thing. We have covered every one of those objectives. Now, along with this video, I'm going to send you a listening guide so that you can work through the problems as I have gone through them. I'm also going to send another worksheet with a whole bunch of stoichiometric problems for you to work through. And the good news is that in every one of those questions, I give you the answers. So the deal is not, I'm not giving the thing away. You need to know what the answers are to know if you've solved it right. So even though the answers are written right there, you want to go through all the steps that we've gone through to actually solve the problem, and then you use the answer on the sheet to check yourself. So you'll be getting that additional worksheet as well.